Welcome everyone. So this is a first keynote of CBSoft. So it's an invited keynote for SAST. So we are pleasure to receive Myra Cohen with us. Thank you very much, Myra, for accepting to be part of the Congress and also to be keynote speaker for this SAST. I will just introduce you and then you can take over it. So Myra Cohen is a professor in software engineering in the Department of Computer Science at Iowa State University. So her interests are in software testing of highly configurable systems, search-based software engineering, application of combinatorial designs, and synergy between engineering systems in synthetic biology. This is quite nice, actually. And of course, she serves as many program committees in journals. And also she was the general chair of ASE and program chair of IST 2019 and ESSEC FSE last year. And also Myra is an ACM distinguished scientist. So Myra, again, thank you very much for being with us, and the floor is yours, or the screen is yours. Thank you.
Thank you very much for inviting me. I'm really pleased to be here today. I'm excited to be at CBSoft and SAST, and perhaps next year I can come in person, but this year we'll have to do it virtually. So today I wanted to talk about what we call the evolution of search-based software testing. Since this is a symposium on automated testing, I thought I would talk about one of the topics that has been really central to some of our ability to be able to automate testing. So let me just start with a very simple software testing problem. So suppose I have a media player, and this media player has three different what I would call features or different configurable options. So this might be a product line, and my media can either be an MPEG or a raw encoding. It can have either audio or video format, and it can have closed captioning turned on or off. So this is a very simple system. And if I look at this system and I want to be able to test this, a test case in this environment might be a series of tests that open specific videos, perform a task, and then evaluate whether that test was correct. And I may have hundreds of tests to run to test this system. But when I actually want to test my, what I'm going to call configurable system, I have to choose a specific media player to use, right? So you can see there's many options here. And so for instance, I might choose a media player that has MPEG, video, and closed captioning off. And I run all of my test cases and these pass. But unfortunately, what happens in an environment like this is that if I make a change and I run those same tests under a different configuration or a different set of features enabled, I may not be as lucky. So for instance, if I move to the raw encoding and I leave everything else the same, I may uncover a bug. And this is a common thing that happens when we have these kind of configurable systems. We have lots of interacting features. What happens is when people build a system, they tend to build each of the components in isolation. And so for instance, when I built the closed captioning, I may not have considered both an MPEG and a raw format. I may have only considered that it was going to be an MPEG format. And so my specifications, when I built the buffer sizes, et cetera, that were going to interact with my encoding may not be large enough, and I may cause a crash in that way. So in this environment, we need to be able to think about how we can explore this configuration space. So in practice, this is a tiny little system, which is why it's up in my left corner, very tiny. It only has 8 possible configurations that we can put it into. So this is really trivial. We can probably build all of these media players and test it exhaustively. But let's look at what happens in practice. So this comes from the Firefox preferences window. If you type about:config in Firefox, you get access to over 2,000 different options that you can modify. And so if you look here, for instance, I'm just searching under window, you can see we have some that are perhaps binary, so they're either true or false. We have others that have values, so these values may vary. We may have to partition these into 3, 5, 10 categories, etc. So we have a lot of these options, and as I said, we have over 2,000 in Firefox. And so if I look at what that means from a perspective of this configuration space, well, I tried to figure out how much 2 to the 2,000 was, but I couldn't find an application that would compute it. So I just did 2 to the 1,000. So we're just looking at half of that space. And you can see this number, I have to move this over 300 decimal points. So this is a huge number. And that's the number of unique configurations if I was to manipulate this entire space and try to enumerate everything in the space. So what are the implications for testing? Well, suppose I have, tons of cloud computing devices and I can run lots of tests in parallel. Maybe we can handle it in that case. But I tried to calculate this for you. So if I divide this into, suppose it takes a second just to run my test suite, and that's probably unrealistic because most test suites, if I'm running something about Firefox, is going to take probably minutes to hours to run, right? But let's just assume it takes a second. So if I look at how many minutes I have, hours, days, years, even centuries, you can see that we don't do much to reduce that size. So these are huge combinatorial spaces that explode. And so this is a problem that we tend to run into in testing these large systems. So our problem here is that we can try to enumerate all of our possible instances, in this case of Firefox, but we can't really do that. So here's a similar problem. This actually comes from, it's a sample program from one of our search-based tools, and it's just a very simple stat class. And if I think about all the possible ways I could interact, all of the potential inputs to this program, or I think about how can I find inputs that cover specific lines, branches, or paths of the program, and I want to perhaps optimize those so I have the fewest inputs or the longest inputs. Again, this becomes a problem where I have way too many solutions to enumerate. So how do I handle a situation like this? I can't just exhaustively go through my space. I need to do something else. I can, of course, randomly search the space, and that's one of the solutions that people have proposed over time. Or I can use something a little bit more perhaps intelligent. And so I might want to use a search-based approach. And this is where search-based software testing comes in. Search-based software testing has been used for many problems. I've given you 2 examples. One is perhaps in this area of configurability, and I'll talk more about that today, but also to generate unit tests, to generate system tests. And so we'll discuss a little bit more about some of that history as well. So in search-based software testing, the first thing we do is we need to have a set of inputs of our system. Then we initialize our system in some way. So we might start out with some random solutions in the space, or we might have some seeds that we know are probably pretty good. We have to define a fitness. Our fitness tells us how good individual solutions are. So if I go back to that example of the media player, and I'm trying, suppose my goal here is to find a fault, and I look at an individual instance of that media player, I have to be able to measure if one instance is better or worse with respect to moving towards a fault. So I have to have some notion of fitness or the quality of the solution. And this is going to vary from problem to problem. Then I have some stopping criteria. All of these search-based algorithms just iterate until they're told to stop. And so my stopping criteria might be some budget of time or number of iterations that I'm going to run. Or I might be able to have some properties of my problem. If I formulate the problem correctly, that will say my criteria is met. And if I do that, then I'm going to output a solution. Now, I mentioned here that I'm outputting a solution to the problem, but I might also output multiple solutions. So we have 2 kinds of primary search that we do. The first is a single solution, and that's what I'll talk about today. But we also might have a multi-objective search. So for instance, we might want to balance 2 competing objectives such as cost and effectiveness, in which case we would provide a set of solutions, and then the user of that system can decide which are the most important. We give them something called a Pareto front, which is basically all these solutions that are not dominated by others. So these are two ways we can actually look at the solutions to the system. Now, supposing my stopping criteria wasn't met, well, then I have to go through a series of what we call operators. And these operators are going to vary depending on the type of search. I'm showing you in this example something that's similar to we call a genetic algorithm, but there are other algorithms that work a little differently, have different operators. But they all are pretty similar in the sort of common features of these systems. So in this case, we have selection. So we're going to choose our best solutions. In a genetic algorithm, we're using a population. So we'll choose the best solution. In a more local search, which we'll talk about later, we might just have our selection might just be choosing a point in the space to change. In this environment, we might do crossover, so exchanging information between different solutions, and then mutation to sort of bring back some diversity into this population. And we continue and iterate over this as we go. I just wanted to mention that these algorithms really come out of, it's a subdomain of artificial intelligence. And I mention that because SBST, or search-based software testing, has been in the software engineering community now for over 10 to 15 years. We've really been using these techniques. And I know there's been a large push now to bring other AI techniques into the software testing community, but I thought I would at least say that we've been doing this for a long time. So some other common SBST algorithms. I just showed you something that looks kind of like a genetic algorithm, which follows evolutionary biology. It tries to simulate how populations of organisms evolve over time. A common algorithm that I've used a lot is something called simulated annealing. This is more of a local search, meaning I start with one solution at a time and I systematically move through the space. It's called simulated annealing because it has, all of these algorithms have heuristics or meta-heuristics that help us try to move around the space intelligently. And simulated annealing has something we call a cooling schedule, which behaves similarly to how we would anneal metal, how we would cool down metal. So it lets us start very randomly in the beginning, and over time, we make less random choices as we get closer to, as the analogy goes, closer to a solid or closer to our solution. Taboo search is another local search that allows us to keep track of previous solutions that we've been made, so that we don't get stuck in cycles, or what we call local optimums in our system. And then ant colony optimization is another population-based search, such as genetic algorithm, that lets us move in a distributed fashion. And this follows sort of nature and how ants forage for food. They leave pheromone trails, and they start to converge on a good solution. They start to put more and more pheromones down. And so ant colony is very good for finding things like shortest path. And it's been used a lot in search-based software testing as well. There are many others, but I just wanted to mention a few of them here. So for all of these, we have some common kind of elements to all of our searches. So first of all, we need a representation. We usually call that our chromosome. And this is one of the challenges for search-based software testing, is how do we take our problem and represent it as a search problem? So we might, for instance, if you think about the configurations, we might just have an array which tells us here are all the possible features of our system, and these are the values they're set to. And a single instance of this chromosome represents one instance of a potential media player. We could also have numbers, and those numbers might represent inputs to the system. So they might represent just inputs to our program. They could also represent parts of a control flow or dependency graph. It really depends what we're testing. And let's suppose they just represent inputs. So we might say, call the application foo and then pass it the numbers in that chromosome. And of course, once we have this, we now have to be able to take this chromosome and measure it with some amount, with something we call quality. So we might look at how many branches are covered, or some other property that we're looking for. For instance, in configurability, we might want to see how many of these different configuration options or what combinations of them we've covered over time. Now, we also need to be able to navigate our system, and this is a very important part of a search. So once I have a set of solutions, you saw in that example of the genetic algorithm, we do something called crossover. So we actually move throughout the space. We need to be able to go from one solution to another and search that very large space of potential solutions. And so what we would do here is we have our initial chromosome, and then we define some transformation function, and that will now let us move to a different part of the space. So here you can see I've just changed a single value from 100 to 20, which is another valid value in this example. Or I might swap two examples. So I might take the 5 and the 100 and swap them. So these are kind of different ways we could navigate through that space. Other important elements we have to worry about when we're thinking about a search is, as I said, the fitness or the quality of solutions. And when I work in a new problem, for me, this is one of the hardest challenges, is coming up with a good fitness that really guides us and has a nice smooth curve. We also have to worry about our operators, our selection, crossover, mutation, all of those meta-heuristics. They're all very important when we design a search-based technique. We also have two sort of competing objectives. So here you can see these are all my solutions, and they're kind of intensifying. So they're all starting to look the same over time. As our search goes from the beginning to the end, what happens is we start with usually a pretty diverse set of solutions. And as we get closer to the solution, we have to intensify so we can actually find that solution we're looking for in the space. But we also have to maintain some diversity in this space, because if we lose all of the diversity, then we don't have that genetic material to modify and change our solution to find the optimal one that we want. So these two competing objectives, intensification and diversification, are very important. And we control these a lot with our other aspects, such as our transformation, but also with tuning our parameters and our rates of mutation, et cetera. And we try to balance these two objectives when we're searching. So we want to keep some diversity over time as we intensify. Now, the goal is to get this really nice smooth curve. So we have a fitness here, and you can see, and we have a transformation function. And in this case, we're going to minimize our solution. We're trying to get to the bottom of this bowl. And so we have a lot of guidance. We have a very smooth curve, and we can, if we put different solutions at different points on this curve, it's very easy to see which one's better than the worst, and we can move towards that result. This is an ideal curve. Often we have curves that look a little bit more like this, where we have these big flat plateau areas. So these are problematic because we get stuck there and we don't have a lot of guidance. So often when we have a space like that, we want to change some of the aspects of our search to make them a little bit, to define them a little bit better so we can get a smoother curve. We might have a space, this is a really problematic space. You can see that we have this big flat area, and basically we have to be lucky to sort of fall, if we're trying to minimize here, our solutions down at the bottom. And so in this case, you can see that we're going to be stuck. So this is not a very good search, what we call landscape, to travel around, because this is going to not give us a lot of guidance. So when we build our search, all of these pieces help us define what makes a search of high enough quality. Now here's some other example, landscapes we might have. So this one on the right, this one that I'm circling is actually from a problem that I'm going to be talking about later. It's a real landscape. These others are sort of idealized. And you can see we might have a landscape where we have some spike and then other sort of peaks. And you notice with all of these, we have what we call local optimum. So in the case on the right, we're actually trying to minimize, but here you can see these others, we could be minimizing or maximizing. Either case, we have kind of curvy space. And so we have lots of places where we might get a solution. Maybe it's not an ideal solution. So we have to find ways. And these are where all of our heuristics or meta-heuristics help us kind of navigate around this space. So this idea of a landscape, and what I've shown you, these graphs are really what we call the landscape of the search. And they're an indicator of the quality or the health of the search. And it shows, where our search can get stuck. And then it suggests numbers and distributions of solutions. So The landscape, to me, is a critical aspect of any search, and I always think about a search in that form. And so there's been a lot of research on this, and these are just some example of some papers, but in general, understanding the landscape of your problem is what allows you to build a better search. And you can modify that landscape. I'll show you an example later on in this talk by changing these various parts of the search, by changing the fitness, by changing your transformation function, by changing those different operators. All of those impact the landscape of the search. So since we're thinking about the landscape, let me tell you a little bit about what I'm going to talk about today. So I've just given you a little overview and introduction to search-based software testing. In the rest of this talk, I want to go back in history a little and talk about where we are with search-based software testing and talk about its maturity. And then I'm going to talk about two examples where first we changed the landscape to reformulate a search to give us better solutions for a specific problem. And then another case where we learned about the landscape, and this is sort of a newer area of search-based software testing. And then I'll just reflect on some of what we've learned today. So I want to talk a little bit about the 40 plus years of history. This is a long time. And this is based on a talk I gave a couple of years ago at the search-based software testing workshop. Now, I started in search-based software testing in the early 2000s, and I probably published my first work in this area around 2003 or 4, but this area has been around for a while, and it's really been maturing. So that was what I was trying to investigate in this part of the work. So many people credit Miller and Spooner from 1976 for the first work on search-based software testing. And in that work, they proposed this idea, but there wasn't a lot of activity in this area. And it kind of sat around and not a lot was done with it until around 1990, when Carell sort of reintroduced this idea and brought back this notion of search-based software testing. And after that point is when it started to really take off a little more. And there were several papers in that 90s, especially in the late 90s, that sort of brought about this idea more of search-based software testing. In 2003, a group of researchers led by Mark Harmon and several others wrote this paper, and this is a seminal paper. If you have time to read this, this was one of the first real papers on search-based software engineering as a problem, and it talked about reformulating software engineering as a search problem. And in this work, they looked at many things besides software testing. They looked at requirements and reverse engineering, but this was really sort of the sort of birth of our modern, what we call search-based software engineering. And there's been follow-up papers, but this is sort of the original one that happened. In 2008, around that time, we were starting to see more tools appear, and a workshop appeared, the Search-Based Software Testing Workshop, which has now been around for more than 10 years. And so that started to happen every year. Right now, that's occurring usually, the last few years it's been with ICSI, it's been associated with other conferences in prior years, and that's still an active workshop. But at that time, a lot of the papers on search-based software engineering, search-based software testing were still being presented in these special conferences and workshops and symposiums such as SBST, which is a search-based software engineering symposium. And then around 2012, we can see that things are changing. And the reason is during that time, many papers on search-based software testing started to appear in all of the main conferences. And ACM gave SBST its own classification. So there's now something called search-based software engineering when you choose the classification for your papers. And of those, about 54% of them are on testing. So really a majority of the papers that we're seeing are on testing. And these are appearing in all of the main conferences today. So if you go to any of our big software engineering conferences, you'll often see at least one session, if not two, or papers sort of spread throughout the conference on topics of search-based software testing. In 2019, Mark Harmon was awarded a prestigious award from IEEE. And I just thought it was interesting because part of it was his contributions in establishing search-based software engineering. So clearly we've gone from over time into something that maybe is what I would consider a mature field. So I went back to ask, can we consider this a mature field now? It's been 15 plus years. We're in all of the main software engineering venues, and search-based software testing is being applied across many areas. So it's used in unit testing, it's used in regression, functional, non-functional testing, embedded devices, model-based graphical interfaces. So it's really expanded, and it's just another tool in our testing toolkit. And that wasn't the way I viewed it when I first started working in this area, but now it seems to be sort of a commonplace field. So have we reached technical maturity? So I kind of decided to think about, well, what does that mean? And I went back and looked at this paper from Redwine and Riddle. This was from ICSE 1985, so that predates my time at ICSE. And what they were trying to understand is looking at what characteristics of a mature technology was. And in this work, they argued that it takes about 15 to 20 years to mature technology, so it reaches the community at large. I think people still say it takes a long time. That number has dropped, and part of the reason it's dropped is because, especially in software testing, is because we have so many open source systems. We have large companies that are supporting research, that are actually doing research, that are providing technology. And so I would say that time has dropped. But I went to look at this article to understand what it meant to be a mature technology. And the irony is that actually, I'm saying that the time has dropped, but it was about 15 years in really using SBST before I looked at this. So perhaps that's a good time frame. So in that, they had 6 different points. And some of the things they talked about was being able to have development and extension of that technology, enhancement and exploration, so sort of going beyond and exploring beyond what that area does, and then making it more popular, so having lots of versions, tools, etc. And so I sort of looked at this and thought about this, and I really think from our perspective, there's probably what I would call these 4 different things. So we need to have tools in software testing in order to make them mature, because without tools, we can't use the tool. Only people that can use them are the experts who write their own. We need extensions. So we don't want to just have the tools, but we want to be able to extend them and go in different directions. Hybrid approaches are important because it shows that now we can evaluate when our techniques are good and when they can be improved, and how we combine techniques, because no one technique is perfect. And of course, we want to have some sort of industry adoption. So I decided to look at this search-based software testing from that perspective. And here's what I found. I call these successes. So first of all, tools. Now, this is not meant to be exhaustive, but these are a series of different tools, all of which perform search-based software testing. So we have, Evosuite, Exist, Casa, which I'll talk about later, Sapiens, Austin, which was an SBST tool. It's one of the original ones. Sushi, TARDIS, DroidMate, I can keep going, but these are becoming very commonplace, and they're available, many of them in open source or some other format for people to use. And there are many that people are developing for their industry partners. And in fact, now when I used to teach search-based software testing to my classes, I used to always have students write their own genetic algorithms from scratch. And I still do that so that they can learn, but now I more often use existing frameworks and libraries because they can do a lot more, because many of these already exist in a form and they can go a lot faster by having that background. So also SBST, which is the testing workshop, has a yearly tool competition. And different people are winning that competition, some from industry, some from different tools here. So again, the tools seem to be getting to be mature. And I'll just use Evosuite, which was one of our software search-based tools. It's not the only one, but I'm going to use it as an exemplar because it's been around for a while and they've really been expanding this. So it started as a research tool. Originally, we only had access to an executable or jar file. It's now open source, which means we can extend it. You can change it. There are many papers that people are expanding on the Evosuite. And this is just for those of you that are not aware, Evosuite is a unit testing tool for Java. that example stack program I showed you came out of their example program. So what they do is they generate user unit tests for classes of Java classes. It's configurable, meaning I can actually change its preferences just like I changed in Firefox. It's extensible. As I said, we can add our own logic to it, add our own search techniques, and people are doing that, add our different metrics and fitness functions. And they've been having conference tutorials, and they've won some competitions. As they haven't won all of them, actually, so, which is really nice to show maturity because other tools are coming in sometimes and beating them. So it's an example of a tool that started and has over the past 7 to 8 years really matured. And I went and I looked on Stack Overflow, and you can now there were 58 questions when I looked, but you can now look for Evosuite on Stack Overflow. To me, this means we really matured because now people are asking questions about them. The second thing I mentioned was technical extensions. So I want to point out this work, and this is not when you consider search-based software testing, although it actually is an extension of this. So this paper, automatically finding patches using genetic program, you may have heard about some of this work. You read some of this work. This particular one was GenProg, and it received an ICSI 2019 Most Influential Paper Award from N-10. And what this work is doing is this is using genetic programming to find patches in software. Well, this came out of the search-based software testing community. This is really an extension. So here we have a whole new field that has come out of search-based software testing. This was some work by Andrea Arcuri around the same time as GenProg, which was also suggesting that we could do the same idea as automatically patch programs. And this is all driven by test suites. There's now a workshop on genetic improvement at ICSI in various years. And so every year they have these different workshops. And there's something called automated software transplantation. So genetic improvement is kind of a superset of this automated program repair. Automated program repair tends to try to solve fix functional bugs. So I have a problem with my program and I find a fault. It does automatic fault localization and then finds patches based using a test suite to guide it. And this is the search-based version. Obviously, this field is also expanded beyond search, which shows its maturity. Genetic improvement is a superset of that where we look at other kind of properties as well. So genetic improvement often looks at non-functional properties. So trying to improve the energy of a program or performance of a program. But again, it's using some sort of genetic programming to do that. Automated software transplantation is yet another variant of this where I may have a system and I want to update, for instance, one of its modules, and I can take software from another system and automatically embed that in the existing system. So all of these are extensions to what we call search-based software testing. Third, we talked about having hybrid approaches or sort of extensions. And so in 2015, Felton Polding said that they had empirical evidence in a paper they wrote, and they showed that no single technique is most effective. So they were trying to compare search and other techniques, and they pointed out the need for hybridization. Now, there have been many hybrid approaches. I'm just showing a few. So this is a concolic and evolutionary algorithm framework. Here's one where we're using symbolic execution, concolic testing, and search-based testing. Here's fuzzing using search-based testing. So rather than being random, it's kind of combining the two. And this is some of our own work where we took Alloy, which is a model analyzer, and uses SAT-based approach and put in a genetic algorithm to do evolutionary computing. So again, I think we're passing that bar of having hybrid approaches. And last, industry adoption. And so this is a key one if we're trying to get a mature technology. And so there have been startups in search-based software engineering, software testing, and many industry players. So I'm just mentioning a few because I don't want to leave out some, but Daimler Chrysler, Ericsson, Microsoft, and the one that right now has a lot of visibility is Facebook, because the group that built Sapience, which was a multi-objective search-based software testing framework for for mobile apps. It was built by Yue Jia and Mark Harmon and their colleague. They brought this to Facebook, and they're now, if you look on the Facebook page, you can see that they have a workflow where they're doing both fixing and finding. So they're first finding bugs and then fixing them automatically. And so clearly industry is adopting this. And this is just one example, there's many others. So I would argue now that I think search-based software testing has become mature. I think we've solved that, but there's lots of open challenges. And so let me mention a few interesting areas to look at. So I don't think we've solved the multi-objective optimization problem. A lot of people are doing multi-objective optimization, but it's challenging because you have to balance multiple competing objectives. You get sets of solutions, and this is challenging. So we can measure how good those solutions are, but you have to be able to help the engineers choose the right solutions, decide which ones they want. And so this is just harder conceptually because we have multiple objectives. So I think there's a lot of work we can do there. We need oracles. Some of the tools pull oracles from code, but when we do automatic test generation, we have a simple oracle if a system crashes, but we may not have the oracle of the actual program itself. If we're doing something like unit testing, such as Evosuite does, they can pull oracles from code, but we often do system testing. And so maybe we have something such as metamorphic SBST. And this is just a suggestion. I think it's an interesting idea, but I think we need to think more about how we come up with oracles, because we can generate the tests, but we still need humans in many cases to give us those answers and what the actual tests should be doing. Human in the loop search is very interesting area. There's been some work in this area, but the idea is that you let the human come in every so many iterations, and they can tell you whether or not they agree with your fitness. So they can give their subjective value to it. They can also say, I prefer these objectives over other objectives. So they kind of help guide the search at points. So the search works automatically, and then a human comes in, provides some feedback, and then the search adapts based on that. So that's another area I think is very interesting. And then two others that I'm going to talk about a little bit now are constraints in the problem space and what I call learning the landscape. So I'm going to spend the rest of this talk just going over a couple of areas I've worked in, which I still think are not completely solved, particularly the last one. So I thought I would talk about them. So constraints in the problem space relate to dependencies we have, and there's been a lot of research on this. So when I have a landscape and I start to have some of my the individual elements of my chromosome can have a dependency on another one, there's lots of things you can do. So some people try to repair chromosomes to try to incorporate those dependencies. If you think about it from the search landscape perspective, some people argue that some of the approaches avoid those. So we just throw out any solution that violates some of those dependencies or constraints, but then we might get stuck and we might not be able to find a solution. Other solutions allow you to have some bad solutions that don't satisfy constraints in your population and then move away from them. So there's different approaches. And so this is something we looked at, and I'm going to go back to that problem I started out with, which was the problem of looking at configurable software. So this is some work I did with a student of mine, Brady Garvin and Matt Dwyer, looking at how we could do, we call constrained interaction testing. And the key here is that we went and we had to change our neighborhood to make this happen. So let's go back to that example of the media player. So we had these three different features, and we know that when the system gets large, such as when we go to something like a Firefox, we have way too many solutions. We can't possibly evaluate them all. So what do? Well, we can randomly, if I want to test and I want to find those bugs, I can build a search to try to find buggy spaces. I can do that. Or what I might want to do is sample the space. And what I might want to do is systematically look at different combinations of features. And the reason I might want to do that is, I mentioned earlier, we tend to have these combinations of things, such as I talked about closed captioning being on and the encoding being raw, that might violate a specification of one another that they didn't know when they built that module. And we know that these kind of, we call interactions, tend to be lower order, meaning they tend to be caused by 2 or 3 different features together. They are more rare to be if it's caused by many. Now, we've seen some that need to have a large number of different features turned on or off to find a particular bug. But in general, they tend to be order 2, 3. So the idea that we might want to be able to systematically sample the space and perhaps let's test all of the encoding and format combinations and maybe all of the format and closed captioning combinations. So let's look at systematically sampling that space. And that's something that's called combinatorial interaction testing. And so in this case, as I said, we have these 3 different features. And the idea is that we want to take all combinations of encoding and format and make sure that we have them here. So in this case, we're going to call this pairwise testing. So we're going to look at all 2-way combinations. You can see that between encoding and format, I have MPEG with video, MPEG with audio, raw with audio, and raw with video. So all of those combinations are there. Now remember, there were 8 different configurations in this full space. So we've reduced this in half. Of course, that doesn't seem like it's a big gain, but in general, what we know is these sample sizes grow logarithmically with the number of features. So if I go back to that 2,000 features, logarithmic growth against that is going to be a big win. Now, we also have to make sure that we look at encoding and closed captioning and format and closed captioning. And in each case, you can see we have video, yes, video, no, audio, yes, and no. So we've covered all of those. So we have a pairwise sample. And so this is how we might build these samples for testing. And so you're saying, okay, so this is a nice way to do this. We also might want to think about not just doing pairwise, what we call T-ways. So we might want to think about perhaps if we have more, we've added some additional features, we would look at all, in this case, 3-way. So we've got encoding, format, and closed captioning. We'd want to have all combinations there, all combinations with these ones I'm not showing you here, all combinations with any of those, any 3, in this case, any 3 of these features in this sample. So how do we find these? Well, it turns out that finding a minimal kind of sample that satisfies this pairwise or this T-way property is also a hard problem. So we also can't just enumerate a space to do that. And so what we've used in the past is we've used search-based techniques. And so this idea of using combinatorial interaction testing to find the samples was in place for quite a while before I started looking at this problem. But let me show you a little glitch with this environment. So I mentioned before that we had these different MPEG and RAW, format, audio, and video, closed captioning, yes and no. But what I didn't show you was that there was a constraint on this system. So this says that when closed captioning is yes, that the format has to be video. And that's because if you think about it, closed captioning probably doesn't make a lot of sense in an audio environment. So there's a constraint or dependency in the system that we didn't consider. And if we look at that original test suite that I showed you that had 4 items, you can see that at least one of our solutions, number 3, raw audio and yes, has a constraint violation. And it turns out that this problem is also a hard problem, trying to build a sample around these constraints. We did some research on this early on, and we tried to take some of our generic algorithms that would build a minimal set for these pairwise samples or 3-way samples, and over 90% of the examples of the rows that came out of that, of the different samples, violated some sort of constraint. And it makes sense because we were trying to compact and to optimize for coverage, not worrying about the constraints. So this makes our search harder. And so we went about to look how we could do this. So let's look at just the search setup. So this is a very simple example. We actually use a local search, something called simulated annealing here. So we have just an array, which is the population of these various configurations of our system, something like a media player. And then we have a fitness, which just counts how many of these pairs or T-way combinations are missing. So we want to minimize. We want to get to an optimal fitness of 0. And then you can see that we have here, we just select a random space in our array and we change it. And that's our move. So that's our transformation function. And this kind of a single change in our array seemed to work very well when we formulated this problem originally. And so that was very successful, and our original simulated annealing was finding very good results. So the idea is that we have, this is what we call our unconstrained environment. We have this first spot, we select it randomly, we decide if we're going to change it, and then again, we select randomly, we decide if we're going to change it. Now, how do we decide if we're going to change it? Well, this is where we use heuristics. If it's going to give us a better fitness, we move to it. If it's going to give us the same fitness, we move, and that way we move around plateaus. And if it's going to give us a worse fitness, then we use, this is a simulated annealing, we use heuristics based on the cooling schedule where we are in that space. The problem is this is what our landscape looks like, and it's very, you can see it's got, this is an example of our landscape for a problem, and it has lots of little spikes. It's also very regular, but there's lots of little places you can get stuck. And so it's a challenging space, but you can see that it's very fine grained. And so this sort of individual changes seems to work well in that environment. And so we had some results that with this landscape, we did very well with simulated annealing, and this was sort of the best known technique for a while. There's other approaches. So let's go back to the constrained version. The problem with the constrained version, if we look at what's happening is, in order to have a solution that satisfies all of these pairs, remember before we had actually a sample of 4. Well, it turns out to satisfy all the pairs, we actually now have to have a sample of 5, because anytime that audio is set, video is set to yes, we have to have video. So in order to cover audio with all of the options, we have to expand this. Okay, so we have this problem here that we have a lot of audios we have this no on quite often. So it's 3 times versus 2, it's unbalanced. And here's what happens with our search space. So when we try to search, if we're in this spot where we have raw audio no, you can see that all of these red paths are places where we're going to run into constraints. And if we make a single change in our array, like we showed you, we're going to get stuck, and we're going to have this constrained problem. Half of our paths are sort of cut off, and so it meant that it was very hard for us to find a solution using our existing approach. The search had a hard time converging. This was a graph of the number of iterations. You can see that it still hasn't converged here, and we're at 4 to the 10 to the 4. So this is a really difficult problem. So instead, we looked at this and we reformulated it and thought, well, what if we change what our neighbors are? And rather than transforming a single spot at a time, what if we change pairs or triples, have a different transformation? And maybe we can try ones that are missing. So we actually reduce our search as we go, reduce the neighbor. So these are some changes we made. And so here now, in this space, we would be changing entire tuples at one time, like 1, 3 to 4, 5, rather than changing individual spots. When this happens, this is the new convergence. And so you can see now, after 300 iterations, we've actually converged on a solution, and this turned out to be a much faster and better search. And the reason is, if we look at the landscape now, because we're moving in pairs in this case, we only have one bad pathway, and we have lots of other ways to move around that landscape. So the message here is that by changing these transformations and changing our landscape, we can move around it better. And this is the basis for a tool called Casa, or Covering Arrays by Simulated Annealing, which does constrained interaction testing. Now, this is just some examples where we're looking at some sizes. Smaller is better, and you can see between these 2 columns, we were getting some better sizes. We also looked at something called breakeven. So assuming we take the time to build our suite, we were comparing this against some greedy algorithms here, because that was the state of the art in constrained testing at the time. These numbers tell us how many seconds it would take to test the entire configuration in order to break even, to combine both the time to build and the time to run our tests. And you can see we have some NAs, but in general, we're under 4 or 5 seconds. So if a test suite takes longer than that, then we're going to break even by using this search. But there's a caveat. If you look carefully at this paper and you look at the data and you look at, we call unconstrained three-way problems. So these are now larger problems. They're trying to cover all 3 ways. Casa performs worse in all cases. So these negative numbers means that it's not doing very well. So although we solved the problem for the pairwise and for lots of the constrained problems, the old tool, which doesn't consider constraints and just flips a single bit at a time, that one seems to still do much better. And so we sort of have a problem. Which tool do we use in order to solve our problem? Well, now we need to understand the problem. And in a mature field, we don't want to do that. We want to hand a tool to somebody and have them solve any problem. So this led to this work called learning combinatorial interaction testing. We're using something called HyperHeuristic Search that I'll talk about. And the idea is to learn the landscape. So rather than construct, use the tool that's best suited to the problem, let's build a generic tool and let it adapt to the problem. And this is work with Yue Jia and Mark Harmon and Justine Petka at UCL. So at the time, there are lots of available tools. This is not meant to be all of them. This is just an example of some of the tools that were out there for this pairwise or three-way testing. And there were lots of results. So this actually comes from the mathematics community where they try to look at bounds. There are sort of direct constructions. How do we build these kinds of systems? So there are lots and lots of ways. There have been tons of papers on this problem in the last 5 to 10 years, which is why we chose it, because it's a very well-studied problem. And in fact, our aim was not to improve over the existing results, but was to build a tool that was good enough, that did okay across all problems. We weren't expecting to ever improve on existing problems. So the problem is one size doesn't fit all. And there was research evidence in the literature at the time. So here's a quote from a paper that said, with all these pairwise testing approaches, the question is, how do they compare? We can't expect each testing organization to hire an algorithm designer to build bespoke CIT testing implementations for each scenario. We need a more general CIT approach. So this was around that same time. So the idea is, we said, let's look at something called Hyperheuristic Search. And this was developed by Edmund Burke et al. And it's kind of a higher level search. So a standard search that I showed you operates on all these potential solutions. So we saw how we mutate our solutions and we change them, and then we ask if they're better. Hyperheuristic search operates not on the solution, but it operates on the heuristics, or those operators that we use. And it uses reinforcement learning to try to understand which of those operators are the best in this environment. And then that operates on the potential solutions. So there's 2 approaches in general for hyperheuristic search. One is generative, where we develop new operators, and the other is selective, where we actually select existing operators. And we chose a selective approach because this is a very combinatorial testing has been around for so long, and people have built all these customized algorithms. We thought it didn't make sense to just have it generate brand new ones. Let's use what's existing. So this is our framework. So we have sort of an outer and an inner layer. So in an outer layer, we have simulated annealing, and we have some initial solution, which is random. And then we apply that to the current solution and update it with fitness and update our temperature. So this is just a traditional simulated annealing, but these 2 areas that are dashed is where we interact with our inner layer. And so here, it tells us what the operator is we're going to use for our transformation, for our move in the landscape. And it then sends the delta or the fitness back to our inner layer so it can decide what the reward is. So what it does now is uses a reinforcement learning agent that now creates a reward assignment value for all of the operators in each time, and then decides what the best operators are. And then we have a set of operators. So we decided to come up with 2 sets of operators. The first one are sort of what we call standard operators. So this single cell change, that's very common. It doesn't know anything about our problem space. It just changes a single cell, as I showed you. We might add or delete a row, or we might exchange information between rows with some probability. So those are our 3 standard operators. And then we tried to use what we call our smarter operators. So we know that we have this pairwise or T-way example. So we might randomly select a missing tuple, find some duplicate in the array where the same tuple is twice, and replace one of them with this operator. We might select a row and change it to be a row with missing tuples added, or exchange out two rows and then take the one with the higher probability, and that comes back. And so we then said, okay, now we're applying this sort of hyperheuristic search. So what we should probably do is let's find as many data sets as we can, because we want all sorts of different subjects. So we went to the literature and we got a set of synthetic subjects that have been published in the literature over and over again for this combinatorial testing. And so we did both for two-way and for three-way. So the SYN2 or pairwise, SYN3 or three-way models. And then there were 30, these last two columns, there were 30 synthetic subjects that were created in our prior work on the work with Garvin et al. And so we used all of those synthetic subjects and they were constrained. And then we also pulled real systems. So these are some systems from work by IBM. They've done a lot of work in combinatorial testing. And so these are real systems and they've provided us with the models and the constraints. And then the last set were also used in the Garvin work, but they were real systems that we modeled, and we modeled the constraints there. And so we pulled all these systems together, and these were, the top group were two-way and the bottom were real two and three-way. So we had lots of different things, two-way, three-way, constrained, unconstrained, and we threw them all into our search to try to see what would happen. So lots of data again, but let's just look at this right side. So these are unconstrained problems. And this is telling us here on this column that I'm highlighting, the diff with what we call simulated annealing. So the simulated annealing was kind of the state of the art for the unconstrained problems. So this is giving us the highest bar of quality. And what's interesting is you're seeing negative numbers here, and we never expected this. So negative numbers means that the hyperheuristic search actually found a new solution, a better solution than our simulated annealing did. And so that's interesting because here we have one where we've improved by 27. So you can see that in these top group, either we're coming out pretty even with simulated annealing or even better. Now the difference with Casa is even greater in some cases, but that's because Casa was customized for constrained problems. And you notice at the bottom, we do have some problems here where, so it's not perfect. We have problems where you can see occasionally we do better. We're doing better than Casa, but the unconstrained three-way, as you saw, Casa didn't do very well, and we still don't reach some of those numbers. So we still have some work to do there. When we look at the constrained problems, here now we're just looking at we ran it through all these different tools and we looked at the best. And in this case, you can see again, we're seeing lots of negative numbers. So surprisingly, we actually found that this hyperheuristic search improved on existing solutions rather than just doing good enough. So that was a surprise to us. So the takeaway was that this hyperheuristic search does surprisingly well for a generalist approach. In fact, it actually did better than our customized algorithms, which was a real surprise to us. For the pairwise samples, it performs as well as the best and finds better solutions in many cases, but there's still some room for improvement on some of the larger three-way models. And so we have room to tune that algorithm. But let's go back to the landscape, because this is the last little part what I want to talk about. And this is all sort of unfinished work, but I think it's really interesting. So if we look at some of the what was happening during the learning phase, these are just two examples. The top one is, I think, a synthetic example, and the bottom is a real example. But what we're showing here is over time, so this axis is going from 85 missing tuples down to 1. So this is as the search increases and gets closer to the final solution. And this one's going from 51 to 1. So this is time in the search. The y-axis are reward scores. So we want to have higher scores. And as you can see, we have the different operators. And so it's interesting. In this first example, you can see operator 5 is really playing a big role in the beginning. Later on, it kind of switches to operator 4, and that seems to kind of take over. In this bottom one, it seems like operator 4 is really persisting across most of the algorithm. And so this can allow us to try to understand more about the space. It was hard to look at these individually, so we tried to look at them together, and we split this into 3 stages of the search. Early, when it's very random, the middle part when it's a little bit closer to the solution, and the end when it's trying to really solve the solution. So early on, and these are across all of our subjects, so these are synthetic 2, reals, and this is the overall number on the right. And so you can see operator 4 and 5 seem to be selected the most in that early stage. Later on, operator 1 and 4 seem to be selected most. And then towards the end, operator 1 and 6. And if you notice here, you can see operator 1 seems to play a lot of role in that very end, switching that single element when we're trying to get that last solution. So this is, again, giving us some information about that space. Here's one final look at this. These are just 2 examples of, I pulled out these systems, and this is just telling me the number of moves made by various operators. You can see throughout the search, we're very heavy on that red, which is operator 1, but we also see some operator 6. In one subject, we're seeing some of 5, and another subject, we really don't see it much at all. Again, the axis is going from the beginning of the search towards the end. So you can see 1 kind of plays a role here a lot. And this one towards the end, operator 6 plays a role. So I'm not trying to extrapolate too much from these 2 specific examples, but I think that this could lead us to something that we might call explainable search. So I think that these hyperheuristic searches give us a lot of opportunity to teach us about the landscape of the problem we're trying to solve. So with that, I'd just like to reflect a little bit. I talked about search-based software testing in this work and talked about its need. I talked a little bit about its maturity and its evolution over time. We talked about need for a better landscape, and I showed an example in a constrained environment, and then this hyperheuristic search that let us learn the landscape. I just want to end with what I think are still open challenges. So we've talked a little bit about constraints. I think learning the landscape is wide open. There's a lot of interesting areas there. I don't think people have used hyperheuristic search as much as they could have, but I think these other problems are still also ones that people can work on. So with that, I'm happy to take some questions and try to see if I can look at the, I don't know if you want me to look at the chat or do you want to ask me the question?
No. Oh, thank you very much, Myra. Actually, I can ask you some questions. First of all, thank you very much for presenting this history of SBST. So it's quite nice to see how things evolved and how things, the direction that they are going on. Yeah, so at first we have a question from YouTube. So it's from Ana Carla Bibiano. She says, thank you so much. That was a great talk. And the question is, what are the main objectives used for automated software testing investigating the literature? So I would add in this question, for example, are the same objectives from like 20 years ago or 15 years ago still being used, or by the new technologies or by the new scenarios they are changing?
A great question. Thank you very much. So I think they're changing. So I gave an example of this combinatorial interaction testing, and I'll just tell you a little bit about its history, and then I'll tell you where I think things are going. So when I first started working in that area, people were thinking about using it for input parameters, for very simple systems, and it's moved to be used now for configurability, for features, for these much larger systems. And so that's kind of evolved. And in the same way, I think our objectives have evolved. So things like fitting search-based testing into the CI framework. How do you handle things like test flakiness in a search-based environment? There's a lot more work on this automated program repair, which I didn't really talk about, but this is really a part of SBST, and part of that is how good your test suites are and how do we generate tests. And so I think that as time goes on, we have some new objectives. And I think today, the sort of continuous integration environment and trying to handle very large changes and large code bases is really more problematic. And also testing things like AI systems and things where we don't have oracles. And I can see the use for SBST in those environments as well. So, yeah.
Good. Yeah, perfect. Yeah. So we also have a question in the chat by Thelma. Thelma, would you like to speak, ask it out loud? Okay. Yeah. Go ahead.
Okay. Okay. Thank you for your nice talk, Myra. My question is about challenges in search-based software testing. I'd like to know if you have investigated the use of machine learning to learn the human profile with the goal of replacing the human in the loop. If so, what are the main challenges you have faced in this investigation?
Great, another great question. So I personally, so I've used learning in this hyperheuristic area. I haven't used learning to replace the human, but there are some search-based approaches now, I think in some of the mobile environments where people are trying to do some learning. In those environments, they tend to be learning more about what they've covered and what hasn't been covered. There's been less on the human side. I did do some work years ago where we looked at and we didn't use learning, but we were trying to mimic users. And we did this via constraints. So we were trying to generate test cases, for instance, in a mobile environment. And we would put in constraints saying, well, a human, if they're going to perform a task, is not likely to click a button twice if they're trying to do something. They're not likely to do those self loops. They're more likely to take a direct path. So they're not going to take a long loop, but they're going to go through in a direct manner to get from point A to point B if they're trying to do that. We haven't done it with learning. I think it's a really interesting idea. I think one of the challenges is getting enough data, being able to get those training sets of how people use systems. But I think it would make a difference because there is a difference between manually generated tests and what we do with these automated techniques. And the automated techniques are very powerful, but they leave the human out. So yeah, I don't know if that answered your question, but.
Great. Okay, so we still have time for questions. Arthur has posted one on the chat. Would you like to speak by yourself, Arthur? Okay, maybe I can ask you. So I'll read it. Is there a specific challenge to apply SBST to distributed software architectures, especially microservices based?
So I think with that, I think the challenge is more of a generic challenge, but I think what the challenge is here is how to model the system and what is your objective. So is it looking at these combinations of the services? Is it looking at covering certain parts of the service? So I think that the challenge is the formulation. And I have seen some recent work where people have been using search, have been using search on those microservices. But again, I think the challenge is how you describe the space. And then are you going to include the search in an automated sort of testing loop, or are you going to do it offline? So the example I showed you using, for instance, Casa was kind of an offline search, but if you want to incorporate it in an online service, then you have to worry about the efficiency of that search and having it work quickly in that environment.
Okay, great. So we have Eliane. Do you have your raise?
Yes.
Okay, you can speak by yourself. Yeah.
Okay. Hello. Thank you very much for your speaking. It's a very interesting work. And my question is about we are facing now new features in software and applications like intelligent apps or intelligent features in apps and new types of connections like IoT, new types of interaction software like virtual reality or augmented reality. And we have already studies in search-based testing applied to attend this new kind of system with non-deterministic output.
So you're asking so here's the problem. I think the question you're asking, just correct me if I'm wrong, is that it's the fact that the output is non-deterministic and isn't going to give you the same answer every time. Is that what you're saying?
Yes, we have these new technologies in software, and it's possible to apply search-based software testing in these kind of systems.
Yeah, I think it is. I think the challenge here is if they have if there's sort of there's two issues. One is the modeling, and if you don't know what potential features are, you have to leave those open to be able to add those in. But I think the other issue is that Oracle problem I mentioned. And so the question is, and I don't have an answer to this, I think it's an interesting problem, is being able to use some sort of metamorphic environment where you have relations. So you generate relations of tests rather than individual tests. So what I've been talking about is generating an individual test and then having an Oracle, either it crashes or you know what the solution is. Metamorphic testing generates sets of tests that have relations to each other. And then from those, you can actually determine whether or not those relations hold. And if you have a large set of metamorphic tests. So I can imagine building a search where you generate lots of these sets of relations. You'd initially, you'd probably still need to have a human come up with whether or not those relations hold, but I think that might be an interesting direction. And I don't know if anybody's doing that.
Yes, thank you.
Okay, so if you have more questions, please, you can write the chat or raise your hand. Actually, I also have a question because, as you presented, we have many works on this domain, and they back for many years. So probably this is something very important, because otherwise you do not survive. But my question is, how far are we from using it in large scale in industry?
So using all these techniques in industry?
Yeah.
Well, so I think I think they are in some places. So as I said, Facebook is using a version of Sapience and SapFix. So they're using from presentations I've seen. Obviously, I haven't been inside there. I don't work there, but I've seen some presentations where they talk about. So they use the search-based techniques to generate the tests, and then with the fixes, they generate potential patches, and then the developer says whether or not that patch is accepted. But they still are using those automated techniques. I think. Some of the groups that are now building fuzzing and doing intelligent fuzzing and adding search in, possibly some of these larger companies are adding this. So I think, I know Daimler Chrysler for years was using search within their testing framework. So I think it's there. I think we probably need more commercial tools to make it to the point where anybody can just pick up a search-based tool and use it. But I think it's moving into industry more and more. That's what I would think. But I'm not inside of industry, so I say that
okay, yeah. Perfect. Thank you. Okay, if people do not have other questions.
Well, I can stay around for a while. I'm happy to answer some chats if you want to send me chats, and I'm going to watch the next set of talks. So,
yeah. So I think people is a bit shy. So let me double check here in there's the YouTube also, there's nothing yet. Okay, let me check my questions here, because I had one question about the landscape analysis. I mean, if you in industry would need to have an expert, to prepare everything, but then you answer us with the HyperHeuristics trying to make it more general. But actually, one question that I was wondering about is, okay, somehow we are using HyperHeuristics to make it more general, but we are also including some more non-deterministics in their search. So sometimes we can see people saying, how do we trust in the search-based software testing? How can we be sure to test the same things? If you include analysis, landscape analysis, or not, we make it more unclear what's going on.
Great, it's a great point. And I think this is why I mentioned this idea of what I call explainable SBST, and I don't know what that is yet, but I've been thinking about that a lot when I look at these hyperheuristic landscapes, because I think that if you can explain to the user why it made those decisions and which operators it used, it might give them information that's valuable to them about their problem space. And they might intuitively understand that and see that, and they would learn more about their problem space because they've probably been trying to test it for years. And it also opens up what's happening and there's less of a mystery. So I think that if we are going to add these more general sort of learning-based approaches, we probably also want to provide information at the end that tells them. But I agree, when any of these systems, when you don't know what it's doing, and that's the problem that happened early on with automated program repair. I think what's happened over time is as people present developers with patches and those developers become comfortable with those patches and they start accepting them, then I think it gains more acceptance. But I don't know of any companies that would automatically patch without first running it through human developers to make sure that they agree with those fixes. And there's also an issue of readability, so you have to be careful. In the early days, some of our search-based tools maybe just picked random numbers. And I know some of the new tools have really made an effort to come up with numbers that a user might use and minimize those to try to provide more readability and understandability. Because I think that with any of these automated tools, if it's going to go to industry or if anybody's going to adopt it, they have to feel comfortable and understand it.
Yeah, it's quite nice, this idea of trying to explain what's going on there. Very, very good. Yeah, and then it's also a trick question, because we should provide something generic that works for everyone, but on the other side, we have to come up with some very specific thing. Okay, so we have a question from Elton. Elton, do you have your mic and you would like to ask by yourself, or? Oh, I can read it. Okay. Is there any studies that compare the effectiveness of search-based tests and other more traditional testing strategies? In your opinion, how do they compare, if they do so?
Yeah, so there have been a lot of studies, and it's going to be specific to the type of objective. So if you go back, for instance, to the search-based approaches that might build those pairwise suites, then those might be compared against random or other types of approaches. And in general, a lot of times, initially, the state of the art is a random, but people have done some of that work that was by Felt and Polding looked at different techniques, and they found that some worked better than others. So there have been, over time, there have been a lot of studies. I don't have all of them here, but there are studies that look at the different techniques, and they have different strengths and weaknesses. As I said, I think sometimes a human-based test suite is going to give you a different kind of coverage of a system than an automatically generated one. And it depends a little bit if you're generating based on the code or specifications. So there is work. In general, I think it's been successful because we can generate more tests that cover more of the space. And so a lot of the studies look at fault detection, and the search-based techniques tend to be pretty strong at fault detection. But I think there's still trade-offs in all of the techniques.
Yeah. Okay, thank you. It seems there's no more questions. So once again, Myra, thank you. Thank you very much. It's unfortunate that we cannot meet in Brazil, to enjoy the weather and everything else. And I could handle you some gift for accepting to talk to us. But yeah, thank you very much. And I think if someone have more questions, maybe can get in touch with Myra by email. The email is in the slides here.
Yeah, feel free to contact me and ask me a question. Yeah.
Absolutely. Thank you. And so now we have some break, and then we just return the technical sessions of SAST, and then we have a final keynote. Okay. Thank you very much, everyone.
Thank you.